A process is a program in execution, meaning that it is loaded into memory and has a program counter that points to the next instruction to be executed. A process must execute in sequential fashion following the order of instruction in the program. A program is a passive entity stored on disk, such as the executable file. A program becomes a process when it is loaded into memory and executed by the CPU. A program can be executed multiple times, creating multiple processes. For example, if you double click on word processor icon on your desktop, you are creating a process that runs the word processor program. One program can also create several processes. For example, if a user is running the same word processor program to open or create two different documents, they are creating two different processes that run the same program. Each process has its own memory space, register, stack, and other resources. The operating system is responsible for managing all the processes in the system and allocating them CPU time and other resources. In this section, we will learn about process structure, which is how a process is organized in memory and what component it consists of. A process is more than just a program code that defines what it does. The program code is also called the text section, and it contains the instruction that the processor executes. However, a process also needs some information about its current state and activity, such as where it is in the execution and what data it is working with. One component of the process structure is the program counter, which stores the address of the next instruction to be executed. Another component is the processor register, which stores temporary data such as operands and result of arithmetic operation. These components are part of the context of the process, which is the information that operating system need to save and restore when switching between processes. Another component of the process structure is the process stack, which is a section of memory that grows and shrinks dynamically as the process executes. The stack contains temporary data such as function parameter, return addresses, and local variables. The stack helps the process keep track of its own function, call, and return. Another component of the process structure is the data section, which is a section of memory that contains global variables. These are the variables that are declared outside any function and can be accessed by any part of the program. The data section is usually fixed in size and allocated when the process is created. The last component of the process structure that we will discuss in the heap, which is a section, a memory that can be allocated and deallocated dynamically during the process runtime. The heap is used for storing data that has variable size or lifetime, such as object created by new or malloc. The heap can grow and shrink as needed, but it may also suffer from fragmentation, which is when there are gaps of unused memory between allocated blocks. The process structure shows how a process is represented in memory and what information it needs to be to execute. Understanding the process structure can help us design better programs and operating systems that can manage processes efficiently and securely. This slide shows how a process is organized in memory. A process consists of different segments that are store different types of information. The stack segment is used for temporary data such as function parameter, return addresses, and local variables. The stack grows and shrinks dynamically, function are called and returned. The heap segment is used for dynamic memory allocation. The heap can grow and shrink as the process requests and releases memory. The heap is usually located between the stack and the data segment. The data segment is used for global and static variables that are initialized by the programmer. The data segment has a fixed size and does not change during the execution of the process. The text segment is used for executable code of the process. The text segment is also fixed in size and does not change during the execution of the process. These segments are arranged in a linear address space that starts from 0 and goes up to the maximum address. The operating system is responsible for managing the memory allocation and protection of each process. This slide introduces the concept of process states and state transition diagram. Process states are the possible activities or conditions that a process can have during its execution. For example, a process can be running, waiting, ready, or terminated. A state transition diagram is a graphical representation of how process changes from one state to another after an event occurs. For example, a process can change from ready to running when it is selected by the CPU scheduler. There are different models of process state that we will discuss in this lecture. In this slide, we will briefly introduce two of them, the two-state model and the five-state model. The two-state model is the simplest model that assumes that a process can only be in one of the two states, running or not running. While the five-state model is a more realistic model that considers five possible states for a process, which are new, ready, running, waiting, and terminated. We will explain the details and differences of these two models in the next slide. This slide shows a process with a two-state model. A process can be in one of the following stages, which are running and not running. Running means that the process is currently using the CPU and executing its instruction. Not running, on the other hand, means that the process is waiting for the CPU to become available or for some other event to happen. The state transition diagram shows how a process can change its state from running to not running and vice versa. There are three possible transitions, which are: first is the dispatch. This means that the CPU select a not running process and assign it to run a CPU. The process changes its state from not running to running. Second is pause. Here, this means that the CPU stops executing a running process and put it the not running state, whereby this can happen for various reasons, such as when the process needs to wait for some input or output operation, or when the CPU needs to switch to another process, or when the process is interrupted by a signal. The third possible transition is the exit. Here, this means that the running process terminates and releases the CPU. Here, it also means the process changes its state from running to exit. This can happen for three reasons, which is when the process completes its task, when it encounters an error, or when it is killed by another process or by the user. The two-state model is a simple way of representing the behavior of process in an operating system. However, it does not capture all the possible state and transition that a process can have. In reality, there are more complex models that include other states such as ready, block, suspend, and etc. The queue diagram is another way of representing the two-state model of process management. In this diagram, we have a queue of processes that are waiting to enter the CPU. The queue is a data structure that follows the first in, first out principle, meaning that the process that arrives first will be the first one to be dispatched to the CPU. The dispatch operation is the act of selecting a process from the queue and moving it to the CPU. The CPU then executes the process for a certain amount of time until it either finishes or gets interrupted by an external event. When the process leaves the CPU, it either exits the system or goes back to the queue depending on its state. The pause operation is the act of temporarily stopping a process from running on the CPU. This can happen for various reasons, such as when the process needs to wait for some input or output operation, or when the CPU needs to switch to another process with higher priority. When a process is paused, it is removed from the CPU and placed at the end of the queue. The queue diagram helps us visualize how processes are managed by the operating system. It shows us how many processes are in the system, how long they have to wait in the queue, and how long often they get to run on the CPU. It also shows us how the operating system can control the execution of process by using operations such as the dispatch and the pause. In this slide, we will learn about the process state in the five-state model. A process is a program in execution and it can have different states depending on what it is doing. The first state is new. This means that the process is being created by the operating system. For example, when you run a program from your terminal, the operating system creates a new process for it. The second state is running. This means that the process is executing instruction on the processor. For example, when your program is performing some calculation or printing some output, it is the running state. The third state is waiting. This means that the process is waiting for some event to occur, such as the input-output operation or signal from another process. For example, when your program is reading data from the file or waiting for user input, it is the waiting state. The fourth state is ready. This means that the process is ready to be assigned to a processor, but is not currently running. For example, when your program has finished waiting for an event and is ready to resume execution, it is in the ready state. The fifth state is the terminated. This means that the process has finished execution and is no longer needed by the operating system. For example, when your program has completed its task and exits normally or abnormally, it is the terminated state. So the state transition diagram shows how a process can move from one state to another state. The arrow indicate the possible transition and the label indicate the causes of the transition. So, for example, a new process can be admitted to the ready state by the operating system. A ready process can be dispatched to the running state by the scheduler. A running process can be interrupted by an event and moved to the waiting state or to the ready state. A waiting process can complete its event and move to the ready state. A running process can exit and move to the terminated state. This slide shows a 5-state model of process scheduling, which is a way of managing how the CPU and other resources are allocated to different processes. A process is a program in execution and it can be in one of 5 states, which is new, ready, running, waiting, and terminated. A queuing diagram represents the queue, resources, and flow of the processes in the system. A queue is a list of processes that are waiting for some event or resource. A resource is something that a process needs to perform its works, such as the CPU or the I/O device. A flow is a movement of process from one state or queue to another one. In this diagram, we have the following queues and resources. The ready queue is where processes that are ready to run are stored. They are waiting for the CPU to become available. The CPU is the central processing unit that executes the instruction of the processes. It can only run one process at a time. The I/O queue is where processes that are waiting for an I/O device are stored. They are waiting for the device to finish its operation. The I/O device is an input-output device that performs some data transfer, which is the process, such as the disk or a printer. We also have the following flows, whereby a process can move from a ready queue to the CPU when it is selected by the scheduler. The scheduler is part of the operating system that decides which process should run next on the CPU. A process can move from the CPU to the ready queue when its time slice expires. A time slice is a fixed amount of time that a process can run on the CPU before it has to give up its turns. This ensures that no process can monopolize the CPU for too long. A process can move from the CPU to the I/O queue when it requests the I/O operation. This means that the process needs to communicate with the I/O device and cannot continue until the device completes its work. A process can move from the I/O queue to the ready queue when its I/O operation is done. This means that the device has finished its data transfer and the process can resume its execution. A process can move from the CPU to a child execute state when it forks a child. This means that the process creates a copy of itself, called a child process, and both processes continue their execution independently. A process can move from the child execute state to the ready queue when it finishes its works and interrupt its parents. This means that the child process sends a signal to its parents process to notify if that it has completed its task. A process can move from any state to the terminated state when it exits. This means that the process has finished its execution and released all its resources. This five-state model is a simplified version of how processes are scheduled in an operating system. There are more details and variations that we will cover later in this course. This slide shows how the operating system manages the processes that run on a computer system. A process is a program in execution and it needs various resources such as CPU, memory, and the I/O device to perform its tasks. The OS keeps track all the processes and their states using some data structure called process control block or the PCB. A PCB contains information such as the process ID, the program counter, the CPU register, the memory allocation, the list of open files, and other attributes of a process. The OS maintains a table of PCB for all the processes in the system. The OS also controls how the processes are scheduled and executed on the CPU and other resources. The OS uses different algorithms and policies to decide which process should run next, how long it should run, and when it should be interrupted or terminated. The OS also handles the synchronization and communication among the processes that share resources or data. The slide illustrates how the OS allocates different resources to three processes, which is the P1, P2, and P3. The CPU is the main resource that executes the instruction of a process. The I/O devices are used for input and output operation, such as reading from a disk or printing to a printer. The memory is used to store the code and data of a process. The virtual memory is a technique that follows the OS to use this space as an extension of the main memory when the main memory is not enough to hold all the processes. The slide also shows that P1 is currently running on the CPU, while P2 and P3 are waiting for their turn. P2 is also waiting for the I/O device to finish its operation, while P3 has requested more memory than it had been allocated. The OS has to manage these situations and ensure that all the processes get fair and efficient access to the resources they need.
This slide explains how the operating system keeps track of the status of each process and resources available in computer system. The operating system uses tables to store information about different aspects of the system. One of these tables is the I/O table. This table contains information about the input and output devices that are connected to the system, such as keyboard, mic, printer, scanner, etc. The I/O table also records which processors are using which devices and how much data has been transferred between them. Another table is the memory table. This table contains information about the main memory of the system, such as how much memory is available, how much memory is allocated to each process, and where each process is located in memory. The memory table also keeps track of any virtual memory or swapping mechanism that are used to extend the main memory. A third table is the file table. This table contains information about the files that are stored in the system, such as their names, location, size, permission, and etc. The file table also records which processes are accessing which file and what operation they are performing on them. A fourth table is the process table. This table contains information about the processes that are running in the system, such as their identifier, states, priorities, CPU time, etc. The process table also links each process to its corresponding entries in the other table, such as its I/O devices, memory segment, and file. These tables are essential for the operating system to manage the processes and resources in a computer system efficiently and effectively.
This slide shows how the operating system manages different types of information using tables. Each table contains information about specific resource or entity, such as memory, devices, files, or processes. Memory tables keep track of the allocation and usage of the main memory and the secondary memory. They store information such as the base address, limit address, and protection bits for each memory segment. I/O tables maintain the status of each I/O device and channel. They store information such as device ID, availability, current operation, and buffer location for each device. File tables store the information about the files that are currently open or in use by the system or the processes. They store information such as the file name, file descriptor, file pointer, access mode, and log status for each file. Process tables store the information about the processes that are currently running or ready to run on the system. They store information such as the process ID, process state, program counter, register, priority, and CPU time for each process. Each process table entry also points to a process image, which is a collection of data and code that define a process. A process image contains information such as the user ID, environment variable, stack, heap, text segment, and data segment for a process.
This section explains what is process control or short-term PCB and what information it contains. A PCB is a data structure that stores information about a process, such as its state, program counter, register, memory limit, list of open files, and so on. The operating system creates a PCB for each process when it is created and uses it to manage the process throughout its life cycle. A PCB has several components as shown in figure 3.3. The first component is the process state, which indicates whether the process is running, waiting, ready, or terminated. The second component is the process number, which is a unique identifier for the process. The third component is the program counter, which holds the address of next instruction to be executed by the process. The fourth component is the register, which stores the contents of all the process-centric registers, such as accumulator, index register, stack pointer, and general purpose register. The fifth component is the memory limit, which is specify the memory allocated to the process and how it is organized. This may include page table or segment table depending on memory system used by the operating system. The sixth component is the list of open files, which show the files that are associated with the process and their status. The seventh component is the CPU scheduling information, which include the priority of the process, pointer to the scheduling queue, and other scheduling parameters. The eighth component is the accounting information, which record the CPU usage, clock time elapsed since the start of the process, time limit, and other accounting. The ninth component is the I/O status information, which show the I/O devices allocated to the process and their status. And last component is any other information that may be relevant for managing the process. So a PCB, what we can say about PCB is a essential process management because it allows the operating system to keep track of all details of a process to perform operation on it, such as switching between processes, suspending and resuming processes, terminating processes, and etc. A PCB also defines the current process of the operating system by showing which processes are active and which resources are being used by them. In this section, we will learn about threads, which are a way of having multiple program counters per process. A program counter is a register that stores the address of the next instruction to be executed by the CPU. A process is a program in execution which has a single thread of execution by default. This means that there is only one program counter for the whole process and only one location in the program can execute at a time. However, sometimes we may want to have more than one location in the program that can execute at once. For example, we may want to perform some tasks in parallel or handle multiple events or requests concurrently. This is where the threads comes in. A thread is a unit of execution within a process which has its own program counter and stack. A process can have multiple threads of execution, each with its own program counter and stack. These threads can run independently or cooperatively with the same process. To support threads, we need to modify the process control block or PCB, which is data structure that store information about a process. The PCB contains information such as the process ID, the state of the process, the memory allocated to the process, and the program counter of the process. If we have multiple threads per process, we need to store multiple program counter in the PCB, one for each thread. We also need to store some information about each thread, such as its ID, its state, its stack pointer, and its register. We will see how this is done in more detail in the next chapter.